And right now Babylon dep on my case.
Oh, Benji, what's up? Can't wait for a fun day for activities. Let's go.
So what do you want to do, dude?
I don't know, I'm kind of tired. Just want to watch some videos or something.
Yeah, just let me go on my computer.
Dude, let's watch this video of the soccer player sliding right across the field. Oh my god.
Dude, let's examine this through physics.
Well, we had to do.
In order to determine Searle's average acceleration, we first needed to familiar ourselves with the dimensions of the field in which his slide occurred on. This diagram is a replica of Wembley Stadium, the field where this legendary slide happened. As you can see, the length horizontally from the point from which Searle slid to the corner of the field is 9.15 meters. However, Searle's slide did not go directly through the corner, as it was about 3/5 from it. In order to factor this into our calculations, we multiplied 9.5 meters by 3/5 and got 5.49 meters.
Campbell was 3.5 meters from the point when he began to slide. We drew these measurements in a triangle to find the hypotenuse, or the length of the slide on the field. We used a 5.49 meter and 3.5 meter calculations in the Pythagorean theorem to produce the hypotenuse of 6.5 meters. However, Campbell's slide did not just end on the field, as he continued about 9 meters off the field. We factored this into our calculations by adding 9 meters to 6.5 meters to finalize his length of his slide to be 15.5 meters.
Now that we have the time of his slide and the length of his slide, we can determine the change in velocity, or delta V. We plugged in our values for distance and time as so, and found the delta V to be 4.89 meters per second. Now that we have the change in velocity, we can use it and the time to determine the average acceleration. The average acceleration of Searle Campbell's slide is 1.54 meters per second squared.
Oh my god, all this physics work is making me really thirsty. Do you have anything to drink?
Yeah, man. I have a Coke in my fridge.
Oh, okay, cool. Oh, thanks.
Dude, speaking of Cokes, I saw this really cool video on the internet the other day. This guy recreated a whole song with different Coke bottles, making different sounds.
With like the glasses?
Yeah.
That's crazy. Do you want to try that out?
Yeah, we should. Let's
Okay.
do it.
Wow, why does it make different tones?
Because when you hit each one of these, a different tone is created depending on how much water is in it. So the one with the least water makes the highest tone, one with the most water makes the lowest tone.
Oh, so you're saying that, like, when I hit the one with the most water, vibrations are sent through the water to make the sound. And this makes sense because the more water you have, the smaller the vibrations and the deeper the tone.
Yeah.
Oh, cool.
Hey, what's Andy doing?
Oh, I think he's playing Xbox.
Dude, we should smack him.
Oh, that'd be so sick. Do it for the Vine, man.
Yeah.
If we take a closer look at the forces involved in this popular prank, we can see that there are 4 forces active. The forces in the y direction are the force of Earth on Andy and the force of chair on Andy. These forces in this direction are equal, yet opposite, as Andy is not floating nor sinking to the ground. Therefore, the sum of forces in the y direction is 0 newtons.
In the x direction, we have 2 forces acting upon Andy as well. We have the force of the hand on Andy and the force of Andy on the hand. Due to Newton's third law, if a force is being applied on an object, there is an equal yet opposite force in the other direction. Because of this law, the forces are equal but opposite.
That was so funny. I feel so bad for Andy.
Yeah, me too.
What you want to do now?
Do you want to go outside? Hang out by the pool?
Yeah, it's a nice day. Let's go.
Yeah, let's go.
Are we gonna go swim?
Dude. Let's roll this tennis ball off the top of the roof and see if it can land in the pool.
Okay, let's do that. That seems like a good idea. In order to figure out if the ball can go into the pool, first we need to measure the distance between the point where it leaves the roof to the pool. So let's do that real quick. It's about 6 foot 3 inches. Next we need to measure the height of the roof. So according to this, it's about 9 foot 2 inches.
Using the values we calculated and the equation for calculating horizontal displacement, we concluded that the ball would fall 1.6 meters from the roof, just 0.3 meters short of the pool.
According to our calculations, this should land short. Let's see. Wow! We were right!
That was some solid physics right there. Do you want to go to the park?
Yeah, let's go to the park. It seems like fun. Dude, I'm gonna go down the slide.
Alright.
Oh, fuck.
Dude, you shocked me. Why did that happen?
Oh, I think it's because when I slid down this slide, I gained electrons due to friction. So my body charge was negative. And with all these electrons inside me, they really wanted to get out. So when I touched you, the electrons escaped through my body and caused a static shock. Now I'm not negative. Dude, the park was so fun.
Yeah, man.
Wait, hold up. Is this your new car?
Yeah, man. It's a 1992 Isuzu Trooper.
That is so sick. How fast does it go?
I'm not sure because I don't have the speed gauge on it. It's definitely well over 100 miles per hour.
Dude, you know what we can do? We can figure this out through physics.
Let's do it, dude.
In order to find the average velocity of Tanner's sick car, we need to first figure out two variables. One, we need to figure out distance, and two, we need to figure out time. We would then use distance over time to figure out his speed in miles per hour. So, Tanner's car's over there, and this is the marker line. So we measured the distance between Tanner's car and the line is 0.02 miles. Now Tanner will get into his car, and we would time how long it takes for him to get from the beginning point to the 0.02 mile point.
After converting the distance in miles into meters and conducting several trials of the time it took the car to get from the point to the other point, we were ready to plug our variables into the equation for average velocity. After doing so, we found the average velocity to be 16.3 miles per hour. Man, that was quick!